something. Yeah, but first, after having learned so much about models, I would like to make a few cautionary remarks. Some of the remarks I want to make, I think, but I want to make another remark that came into my mind only recently. I mean, you may all have heard of Eratosthenes. He had developed that sieve to determine prime numbers up to some number n, 1000 or whatever. He also measured the circumference. I put it in here. This? Thank you. And I have more chalks?
Now you do have chalk.
Okay, thank you. So he determined the circumference of the Earth. His model was that the Earth is spherical and that the Sun is really far away. He knew that in Syene there was a deep well, and at midsummer night, midday, the Sun shone directly into that well. So it was directly in front of the well. Then he was in Alexandria, a few miles further north, and what he did, he put a stick up here, he measured just the length of the shadow. And from this, he concluded something about the circumference of the Earth. And if we understand the units of length more or less correctly, he came very close to 40,000 kilometers or 25,000 miles. Just one single measurement and a good model. We think it's good nowadays. We know even it's correct. At about the same time, that was 200 BC, something like that. At about the same time, the Chinese also were very good mathematicians. They could have done all of that. And they had also a model for astronomical things. Their idea was that the Earth is completely flat. And the Sun somehow goes around here, has the highest point in the south at midday, and so on. And they tried to determine the height of the Sun above the Earth. And assuming this model, they realized they just have to put somewhere here two sticks, one exactly north of the other, or south of the other, and measure the shadow. Here, that will be a bit shorter than this one. So you measure this length, you measure this length, you know this, and then, of course, using some simple trigonometry that they all knew 200 BC in China, you can measure the height of the Sun above the Earth. Perfectly correct. The only problem is that this model, now we know, wasn't that good. So even though the mathematics was perfect, and it's interesting also to learn more about how the Chinese did that, it doesn't help much. It doesn't really tell us much about the Sun and the Earth. So the model, even though the mathematics might be great, better be correct. So now I come to the model I have been talking about quite often, so some of you know already. It's not my model. It's a model of the theoretical physicists. The theoretical physicists have developed the theory of the horse. And the basic assumption is the horse is of spherical shape. And from this assumption, they can easily develop sort of a theory that tells us, and the guy who wrote this on shape and form, on Darcy Thompson, 1920 something, he really sort of discussed intensively that very small mammals need much more food per gram of their body weight than large mammals. So let's apply it in particular to our spherical horses. The point is a small horse, in a small horse, the relation between the volume and the surface where warmth disappears is of course much smaller. Yes, they are small, more volume, more surface per volume than for a big horse. Therefore, small horses, you have to give small horses more food per body volume than big horses. They can live with less. Absolutely correct, and nothing wrong with it. Darky Thompson actually discussed this in a more general context and gave statistics on how much is being eaten by small warm-blooded animals, birds and mice and so on. This model can also be used to derive another consequence, which actually, if you look into nature, is more or less correct. Horses will always be found at the bottom of a valley. They're spherical, so they roll down. And if you look where they are, you find them there. But okay, then if you look how they move, you may get some sort of not on constant speed, but in speeding up and down, you may get some idea that maybe they are not really, they are spherical shape. We stick to our model. But maybe the density within the shape of matter is not the same all over. So you allow a certain number, still to be specified, k, of small spheres within the big sphere of higher weight. So you may be interested to determine exactly how many there are and of which weight. And you can then develop, you can use maximum likelihood theories by which you compare the possible movement of such spheres with the movements that you actually see horses do. Maybe you come up with just two such spheres of higher density are sufficient, or four, or whatever. Still, we all know, feel, and I mean, that's not a matter of knowledge, it's a matter of feeling. You are absolutely sure that's a bad application of this model. You better look twice how models are really shaped before you develop such intricacies. And now you pointed very clearly out that for the statistical models you need IDD. Okay, you can have different classes and so on, but basically you make very definitive and strong assumptions of which we all know they are wrong. Yes? Now the question is, are they wrong as the spherical horse model is wrong for deducing the amount of food that is required? Then it's not so bad. You still get the general idea. And I would think most of the models we have been talking and learning about this afternoon are of that kind. Horses are not really spherical, but the relation between volume and surface is correctly modeled by assuming it's a sphere. You can even come up with the more general concept that all you need for this is not that they are of spherical shape, but that they are of smooth shape, not fractal. Once you get to fractals, you get another problem. So therefore, Darky Thompson is justified, even though horses are not of spherical shape. But one really has to be careful with model assumption, and even the nicest mathematical theory that you can develop to work with your model assumption does not say anything about whether your model really is sufficiently realistic or not. That's why I asked you also for explicit examples. After all, the proof of the pudding is in the eating, and you have to use this wonderful mathematics that has been developed there over the last 15 years or so. Phylogenetic invariants were discovered, I think, 20 years. 80? 87. So, okay, so we celebrate 20 years of phylogenetic invariance this year. In spite of all this wonderful mathematics that had been developed and the much better understanding of how sequence evolution could be modeled, it is still, you have to apply the theory to real data and try to decide something. I mean, as the inventor of phylogenetic invariance, this was Jim Lake, and others. Okay, always all and others. Jim Lake. I mean, I think he used them to prove that there are really three different kingdoms of archaea, trying to contradict what Böse had said. There's only one kingdom. Whether this was right or wrong doesn't really matter. At least he drew some conclusions from his theoretical assumptions of that there should be invariants, and there are invariants. So this is something I'm missing. I mean, luckily, we are not in the string theory group. There's a relationship between theory and experiments is even much further. I think Mike told me that there is a book entitled "Not Even Wrong." That is, for these theories, you cannot even decide whether, you cannot say they are right, you cannot say they are wrong. There's no way even to describe how they can be tested. So we are in a better situation, and I think in a few years, people will have been using these ideas you were talking about to actually work with real data. And so computer scientists will have devised good, and numerical mathematicians, I think, will also be needed to develop good techniques so that that can be applied. And then maybe certain things that we are not so clear about will be answered in a more definitive way. But now maybe we can start with something here. I will just show you. I did that in that very same room a few days ago already, and I hope it will all turn up. Yeah. Okay, but nothing is here either, so it doesn't matter. Yeah, now we see something. Okay. Yeah. Good. Okay. So you know that, of course you know, that Darwin was born, it's also important, 1808, 09. So in a few months, less than 24 months, there will be birthday celebrations in Darwin and special exhibitions and so on. Not at the herbarium. But he published the one book. I mean, he wrote so many books, but the one book of Darwin, which revolutionized biology in 1859 on the origin of species. And in 1856, Ernst Haeckel, who immediately became an ardent supporter of Darwin's theory, published his book on general morphology, a 2-volume book with about TAF, that's for table, Tafel, with about 20 tables of phylogenetic trees. So these were the first attempts of drawing really phylogenetic trees. Darwin made sketches. All of you may have seen, you find them in the internet and so on, but they were only theoretical sketches to fix ideas. How could it have happened that from some origin it evolved, it branched, it evolved, it branched, something died out and so on. So he tries to fix ideas. But Haeckel really sat down and constructed just drew 20 such phylogenetic trees. That's a phylogenetic tree that's what we are talking about here in this afternoon. How did you call it? Yeah. That's it. This is just, I probably have to do something here. This is just the mammals. You see, the mammals are somewhere up here, very small group here. Here are the birds, here are the reptiles and so on. here are the amniota. Here begins the amniota, and so on. Here are Homo sapiens, even very clearly recognizable. Here are both the cows. Here are Cetacea, the whales. Here are Perissodactyla, that means horses, and so on. And so this tree, more or less, depicted how people understood family relationship between species at that time based on similarity analysis of them. So actually whales in embryonic form have legs that have hooves, I think you call it in English. Yeah? Hooves. And they're not like hooves of horses, but they're like hooves of cows. So they decided that the whales are relatives of the cows, and if you go down here, they are closer relatives of cows than the horses are. And current day molecular biology has fully supported this hypothesis. People at that time assumed that carnivora are closer to primates than these guys up here, which seems not to be true. Carnivora are rather closer to cows than to us. But so what? It was the knowledge of his day. He didn't do any research for this. He just had to know what other people had done since Linnaeus and before Linnaeus, since people came up with such systems, classification systems for species and taxa and so on. So now the problem in phylogenetic reconstruction is, how do you come up with such a table if you cannot just find it somewhere else? If you have information about it, like Haeckel had, he just looked at sort of the classification provided by Linnaeus and his followers, and he could easily draw this somehow. But if you don't know, how can you reconstruct such a tree, or from which data can you reconstruct such a tree? And there's one simple theorem in mathematics that says if for any two leaves, I mean most of these leaves are of course really labeled. You think this is a current day taxon, this is a current day taxon, and if for any two such labels you would know the length of the path from one to the other, and then you get a big distance matrix for any pair of taxa you put in this length. Of course, if for taxa y being x, the distance from x to x is 0, and for all other ones it is just what it is here. This is very small, this is much longer, and so on. So the amazing fact that was discovered already in 1960s or 70s was that this tree in its sort of overall metric structure is completely determined by the distance table, giving for any two species the length of the path within that tree. I mean, that's, once you know it, okay, it is not very hard to prove. But it is still, when I first realized that this is a fact, I was struck and I was quite amazed. And I wondered sort of then how from the distances can we reconstruct the tree. You have also heard today about the topology of trees. Sort of, we really don't want to know exactly. Reconstructing the tree means for every little bit here of branch from one to the next branching point, we know the total length. Okay, we are happy when we know. That means also something for your invariance. But for the topology of the tree, all we want to know is if we cut any such edge, then we get everything up here versus everything down there and up somewhere else. Then you get a split. So that once you cut in a tree, you cut a branch, the tree falls apart into exactly two connected components. Some species are on one side, some others are of the other side, so you get a split. And as there are many branches that you could cut, you have many splits. And again, a well-known result from the 1960s or so is that the topology of the tree is completely encoded by the collection of splits. And this is even much closer to what how biologists seem to think about species or groups of species. Really, biologists want to separate the birds from the non-birds, the mammals from the non-birds, the primates from the non-birds. They always think in terms of splits, the gram-positive from the gram-negative bacteria and so on. You try to separate into disjoint groups. And that's what you really like. I mean, you are happy that the birds and the mammals are disjoint. Because, I mean, there are, so first of all, no bird is a mammal, no mammal is a bird. Furthermore, there are certain animals that are neither bird nor mammal. A problem in phylogenetic analysis would arise if you would have a species that is simultaneously bird and mammal. Then this classification system wouldn't really work. You wouldn't know where to put it. Is it a bird? Is it a mammal? So when the first platypus was discovered, somewhere here, I guess here, Echidna, these are certain eagles, but there are also the platypuses. And the people from Australia gave notice to the people here in England. First, people thought that's just a hoax, can't exist, because it had a beak like a bird, and it had fur like a mammal, and it laid eggs like a bird, but it sucked its young, it gave milk to its young, so it was like a mammal. So Royal Society didn't believe that this existed at all. It took a while until the platypuses were accepted as really existing things, and then classified correctly as relative of the mammals. Actually, we now consider them to be mammals, but not of. There are two big classes of mammals. One are the, you must know, you are biologists. No. Die Beuteltiere und die placentals and marsupials. So there are the placentals, and they are neither this and this, and nobody knows really where they belong to. Apparently there are closer relatives of the placentals, but we do not know. We want to classify the beings we have, and we want to, of course, have a good classification, but any classification provides some insight. So in the old herbal books, the Kräuterbücher from the 16th century that appeared immediately and collected all knowledge that was available after printing had been invented, maybe even in the early 16th century or 15th century, yes. I think printing was invented in the 15th century, wasn't it? They classified beings according whether they can fly, like insects and birds and bats, or whether they have 4 legs, or whether they swim. So another kind of classification, which makes sense in a certain way, but it turned out to be biologically not terribly relevant. But anyway, first of all, we want to classify things. So we could look at cytochrome C, this molecule that had been investigated very early, already by Walter Fitch and others. And you can align all it, and then you can classify into those species where the 10th position in the given alignment is a certain kind of amino acid, say polar amino acid or non-polar. Then you have a nice split. It's not so clear how relevant that is from a phylogenetic biological point of view, but at least all these sequences give you a large amount of splits. And if you find the right splits, let's see whether that comes back, then you can construct, it comes back here now, it will come back there, I guess, sooner or later.
Yes.
Okay, if you find the collection of all right splits, then this tree is completely determined by this collection of splits. Now, these facts, when I discover, I sort of recognized them to be true. Later, I also found them in the textbooks. I found quite intriguing, and I tried to better understand what was going on. So, first thing is, how can you construct from the distances, how can you construct the tree? And as a step in between, from the distances, how can you construct the splits that correspond to the various branches that are relevant? Now, you find something about that? No. In a book by Darwin, not the book, but one book by Darwin, as we have no record of the lines of descent, the pedigree, that's how he called the phylogenetic tree, can be discovered only by observing the degrees of resemblance between the beings which are to be classed. So to me, this is sort of already hinting at the fact that once for any two beings that we want to class, their genetic distance, the degree of resemblance, or conversely the degree of non-resemblance, then we can discover the pedigree. So how does that really work? And now I would like to stop this again. Maybe you can roll this up again and turn to the blackboard. So what we can start now is we have our set of objects, taxa, proteins, whatsoever, and we do have some matrix that is for any 2 points x, y, we have associated the distance of x, y, which I also write for short x, y, and we have just the standard relationships, xx is 0, and we have the xy plus yz is larger or equal to xz for all yz. If you write it in this way, then yeah, you have everything else follows. So this is to get symmetry and so on, and it's larger or equal to 0 and so on. So you have these conditions on this matrix D. So this means it's a metric, or some people call it pseudometric, whatever. And starting with this, assuming that it is the metric of a tree, how can we construct the tree? How can we construct the splits? And this was looked quite difficult, but was much easier than I thought. I wanted to say something more about this problem. So how did I come across this problem? Given this thing, how can you construct a tree? So that was many years ago that Manfred Eigen tried to reconstruct the tree of transfer RNA. And okay, he was interested in the origin of life. So he realized, everybody would have known at that time if he would have thought about it, that there must have been some transfer RNAs in the first living cell. So they must have been swimming around in the primordial soup before some molecules of what was swimming around there were all put into one membrane to form a cell. How did and there must have been more than one transfer RNA because you needed more than one protein. Of course there are. many different transfer RNAs, but they're all similar. So the question then was, can we say that this similarity is due to the fact that that there was one primordial such molecule, pre-transfer RNA, and by standard process of selection, mutation, and replication, the whole family of transfer RNAs arrived that were needed, maybe not 20, but sufficient, maybe not even 61, but sufficiently many, arrived to be incorporated in the first living cell? Or was it rather that there were many such molecules? And the first sort of forms of life just grabbed into this ocean, took this, they're all similar, and then used them for producing a living cell. So are they similar for the same reason while a whale and a dolphin are similar, or are they similar for the same reason as a dolphin and a tuna fish are similar? Because they have adapted to certain functions that are required. And so Manfred Eigen began looking at 3 transfer RNAs. Maybe they had 1, 2, 3, and now I really write down a distance table. Or this always is 0, and assume that this is 2, this is 3, this is 2. And of course symmetric, it's also here the same thing. Then you could say, okay, here is 3, has distance 1 to 1. Or let's start with 1 and 2. 1 and 2 have distance 2. Now 3 has the same distance to, has distance 3 to 1, and 1 and 3 has distance 3. Okay, so this is already distance 3. And now I put probably 2 somewhere in here. Maybe I have that.
The lengths are about 1.
Yeah, I would like to have this of length 2, and this is 3, 2. I corrigate. Okay, then this is 2, and this is 3, and this is 3. So he came up with such a diagram, yes? And now he looked at the force sequence that was, for which he had really the nucleotide sequence. And so he looked for Hamming distance, and he found out that this was distance 3 to 2, distance 3 to 3, and distance 4 to 1. Now can I fit it in somewhere here at the appropriate place? And if you try to do so, you see it doesn't work. If you fit it in like that, then it has a correct distance to 1 and 3, but not to 2. If you fit it in like that, it has a correct distance to 1 and 2, but not to 3. If the only way of doing it is this. So he stumbled across this problem. Actually, all he saw was there are 2 ways of fitting in 4. One is this way, and one is this way, and they are not consistent. So that's when he called me up and said, can you come to Göttingen? I realized that you were interested in working on new problems from biology. I had told him before, so I went there and he told me this problem. And then I began to think about what went wrong with the data. And of course, that's a long story, which is well known, that you need a 4-point condition for a metric to be fit into a tree and all that. But I was much more interested really in this figure that represents the data exactly. because I could not insist that the data would be tree-like. For the transfer RNA, if they had one common origin, okay, their distances should be tree-like. If they were all similar by sort of parallel evolution, by adaptation to the same environment, like tuna fish and dolphin, I cannot insist that there is a tree. So I had to develop a method that would construct a tree if there was one, and would be well aware of the fact that there was no tree if there was none. And it turned out that the right construction is what we now call the tight span of the metric T. So we look formally at all maps F that go from X into R, sort of being virtual distances of the point F, which should have the property that Fx plus Fy is always larger or equal to Xy. That means sort of the virtual points of the tree we want to construct should have the correct formula. So whatever point we have, if it is here, for instance, the distance to 1 and the distance to 3 should add up to something that is at least as large as the distance from 1 to 3. But not necessarily any larger. What you can then say is you are really interested in those f's. If we have one such f, every larger f will do. So the larger ones are not interested. You just take the minimal ones. So we take the minimal ones. That can be characterized another way, but that's better to understand. So we look at this, we call it tight span of D. And it then turned out that this is in case your original metric fits into a tree. So you would start with the Haeckel's tree. You would really measure the distance for any two leaves of that tree that you see in this image. And then you put that in here, and then you construct this. This is exactly all the points in the tree. What means is all the points in the tree. If this is a tree, and you take an arbitrary point somewhere, not necessarily a bifurcation point, just some point, P, then you can associate the map F of P, because we called it F over there, which maps just any x onto the distance of x to P. This will surely satisfy this, and because of minimality, it cannot be somewhere here away. This is impossible, and actually it makes up exactly the points of the tree. So we can reconstruct the tree from the distance data if they are nice. Yes. However, independently what it formally means that they are nice, we can anyway, this construction works in any case whether or not our distances fit into a tree or not. Actually, what this construction gives is it gives a subset of R to the x, a linear space with a metric. Actually, the metric we are interested in this case would be the L infinity metric, the supremo metric. And it embeds, it's a subset here. And as a subset, it is connected, even contractible. You can contract it on one point within itself, the concept from homotopy theory. And yeah, that's it. So if it has dimension 1, it would be a tree. And it would be exactly the correct tree. So this space having, as a subspace of here, having dimension 1 just means that D is a tree metric. And otherwise, it has larger dimension. For instance, if it's here, this is the space for this metric that we did right here. So there are these points all over here, and it has a two-dimensional component. So, but as Manfred Eigen told me, you should not necessarily presuppose that there is a tree. You should just try to find out whether there is a tree or not. I was very happy with the fact that now this exists and is still contractible as any tree is, it is not not necessarily a tree. So my question then was, what is it? Is it close to a tree? What can we do with it? How can we find the splits that we want to have for that tree, for the corresponding to the branches of that tree, if it is a tree? What else would we get if we would look for such things? And so that was 25 years ago that I began working on that. By now, many other people have joined in, or a few other people have joined in, and more insight was produced just regarding this construction. But even better, it is not 25 years old, it is much older. I think now, yes, 67 it was paper, so it's 40 years old. And this construction was provided by John Isbell. Then in University of Washington at Seattle. Later he went to Buffalo, and he came up with this construction in a completely different context. He looked just at metric spaces. At that time, 40 years ago, categories were the newest fashion of the day, and so he wondered whether metric spaces form categories in a nice way. Okay, there are two ways to make them form a category that are both bad. You can just say continuous maps between, there are too many of them. Or you could just say isometries. There are not enough of them. He just said non-expansive maps. So if I have a metric space here, another metric space here, I have a map from here to here. And when a map is a good map, is a morphism, if 2 points of distance d are mapped onto 2 other points of distance d prime, never larger than d. Could be equal or could be smaller. And in this strange Isbell's category of metric spaces, this construction came up, and he came up with it, because these are the injective hulls of metrics. So in this category, every object, have whatever injective hull means, has an injective hull, and that's it. So you look at it as a metric space with respect to the L infinity metric, and you embed X into here by a map that was constructed already by Kuratowski in the 1930s. You map X just onto the map that we now call K sub X, and that maps a Y in X onto the distance of X and Y. So somehow what you do here, P is also mapped onto the distance, P mapped on a map that maps X onto X by P. So it contains X, it is a metric space, and in this strange category of Isbell's, it is the injective hull according to category theory. So I didn't even discover this first. I learned later that Isbell had done it. But so the only thing that I really proved in this context before anybody else did was that if D satisfies this funny 4-point condition, which is necessary and sufficient for fitting into a tree, then this is a tree. And more or less that can be reformulated also as saying that the famous R trees that have been discovered had been considered also in the 70s by Hyman Bass and other people interested in sort of geometric group theory, are injective objects in Isbell's category. Okay, that's just true, but neither side had much advantage of this insight, but it's just a nice fact. What can be said now about this T of D? First of all, how can we get the splits? So splits are just pairs of two non-empty sets A and B, whose union is all of X and they are disjoint. And when is this a D-split? that is, it corresponds to a split of the tree, then this is the case if and only if for all A prime in A and for all B prime in B, you have A prime plus B prime is smaller than A B plus A B prime, which actually for a tree-like metric is the same as A B prime plus A prime B. So as these two must be the same, so we have this must be smaller than one of those, or both of those, but really sensible definition apparently is saying it is smaller than the maximum of the two terms. So this is the most generous we can be. One of those two terms can even be smaller, but the maximum must be larger than this. Then this is a good split.
You allow equality?
Hmm?
You allow equality?
No, here I don't. Here I don't. But what I could prove then is to every split you have this metric delta AB, which just maps xy onto 1 or onto 0 if x and y are both in A, onto 0 if x and y are both in B, and to 1 else. This is a split metric. It just separates a point in A and B. And what we can show is that every metric D is a sum in a canonical way over all D splits S, alpha S, delta S. So I just called it also delta S if this split is called S. With alpha S that are completely determinable by the metric D plus some unsplittable remainder. So this is split decomposition theory that tells you you have this decomposition, and this is canonical in a way and cannot be the main point what you need to prove is if you take away one such component for just one from D and you apply split decomposition to the rest, which is still a metric, then you get exactly all the other metrics. So it is sort of has certain invariance properties which makes it conspicuous. And if the metric comes from a tree, these are exactly these splits are exact, because then we have equality here, it doesn't matter what I write. These are exactly the splits that correspond to the edges. And this is really, I mean, what does it mean from a metric point of view? You have all these splits corresponding to the various branches. They have certain lengths. This alpha S is really the length. And if I have some point x here and some point y here, their distance is just the length of all those splits, or all those branches that separate x from y. This is exactly what you are counting here. If x is distant from y, separated by that split, then you get 1 times the length, and otherwise you get 0. So you reconstruct this way the splitting of the metric into a sum of split metrics that is suggested by this drawing. So all that fitted together very well. Nice. Now this I developed together with Hans-Jürgen, bundled many years ago. I wanted to say something about our current work that I do with Vince and Kati and Jack Coolen and maybe others. We got to look at that from another point of view. If you look at the tight span of not necessarily tree-like metric, you sometimes find something like that it looks like this. Okay, we have seen this then here. So here are sort of blocks, and here are individual points. So this is very well a tight span of a metric on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. That is exactly sort of the metric you see inside here. So the distance between this point and this point is exactly the length of this and this and this. And the distance between this point is the length of this and this and this and this and so on. So, okay, that doesn't seem too bad for phylogenetic analysis. It would tell us that these form a clade, even though we don't know in which order. These form a clade, even though we don't know in which order. These form a clade, and also probably if I join this with this or this with this. So I see certain splits that might be phylogenetically relevant, certain decompositions of the total set into two disjoint subsets, while there's nothing that would sort of separate this from the rest, or this from the rest, at least not really by just one point. So the question is, can we, given our metric D, can we find those points F in the tight span that separate the space? That is such that if I take the point F away, then I get at least two connected components in our span. So these we call cut points, and we can prove that F is a cut point if and only if a certain graph gamma F is disconnected. So what is this graph? The vertex set is just a support of F, which generally is all of X except if this is really a point of our ground set X. And what is the edge set? Now I'll give it a name E of F to define it somewhere else, where I still have room for this. Maybe here. So what is E of F? Again, we have a nice definition for this. We say all the pairs of points x, y, after all, I'm in a subset of X, a support of F, such that f of X plus f of Y is larger than xy. We sometimes want it to be equal because we want it minimal. But of course, if I take this point F and I take X and Y over here, clearly the distance from X to F, from Y to F, summed up is larger than the distance from X and Y, because we can do it here. So in this case, so we can construct this graph that is easily written down, and then we say which points F create disconnectivity, just those for which this graph is disconnected, and for a graph that's much easier to decide. Then it's a graph with a given vertex set, no problem. Question is, can we compute the cut points? I mean, that's a nice definition, might make sense. Actually, yes, we can compute it in with a polynomial algorithm. I think the first version of this algorithm had was maybe polynomial of degree 8 or 7 or 6 or 9 and so on. But then Andreas Spillner, is he here or has he gone home already? He has gone home, but he was here. The thing. He realized that if you do really careful bookkeeping of what we were doing, you can do it in n to the 3, which means, of course, it's much better than n to the 7 if n is getting larger and larger. It's still not linear, but okay, probably as we rarely have cut points. That's the next problem. it will be much faster because this algorithm will soon tell you there's no cut point whatsoever. Because this being disconnected is a very non-generic condition, as being a cut point in a metric space is a very non-generic condition. Once you have something around it, it can't be a cut point anymore. So what we are now studying, and that's still, this is written up, but what we are really trying to understand is, okay, I do not want to look for just points that are cut points, because there are too few of them, so if they are, they would be phylogenetically relevant. But something where if I take out a little disk around it, then the space, the rest of the space, disconnects into different connected components. For some epsilon, these would be, if this would have this disk would have radius epsilon, or this ball, whatever, then we would call an epsilon cut point. And what we really now want to develop is an algorithm that would allow us to compute epsilon cut point. Now I have only 2 minutes left. So if we can try whether this thing comes up again, I can show you some images of metric spaces and their tight span, or projections of these things that yeah, I see it, you can't. Okay, but you will see it soon. Oh, it's too far, going too far. Too early to thank you for anything. Okay, you see, these are the 16 sRNA of which the sequences had been available already 20 years ago. And this is sort of a projection of the tight span. So it's amazingly tree-like, but it is not exactly tree-like. You see here sometimes these parallel edges which show you this is a split. This even is an epsilon split, if epsilon is sort of the thickness of this thing, but it's not really a split. Here this is tree-like, this is tree-like. Also this most contentious edge which separates the three archaea from the world. Jim Lake is not too happy with that. Wöse is very happy with that. But this is very thin. Actually, to make this drawing and to make you aware of the fact that some of these edges are parallel edges, are really, that's not just a tree. I had to overemphasize the distance between these two things, sort of the thickness of these things. Quite nicely you see, and that was discovered, of course, by those people like Wöse who sequenced 16 sRNA, that the chloroplasts over here are close relatives of eubacteria. Anacystis nivolans is even closer to the chloroplasts than E. coli is, or Bacteria subtilis. But from our present point of view, I would like to go back to analyze these distance data that we have, and to use our yet to be written algorithms for computing epsilon splits to show that this is an epsilon split. While the other split that you see here, somehow the split that goes up here and continues here and somehow over here, that separates, that puts all the things together here, the mouse together with two kinds of archaea against the rest. There is a split. But this is apparently not epsilon split and probably not phylogenetically relevant. So that means the story of the tight span construction is not all over, even though the first paper about it was published in 84, and there are still interesting questions to be raised in this context, which in a way is model-free. Where are the models? The models are, of course, in the distances we use. Using Hamming distance as a good distance of genetic distance, as a good description of genetic distance, is sort of a model assumption. But that's where it stops. And if you are not happy with that model assumption, you can try to correct this thing. There are these very early corrections that said if you measure a long distance, the likelihood that the actual distance is longer because there may have been some parallel or back mutations that you don't see if you look at the distance. You can just correct your distances. You can use a much more elaborate methods that had been developed in particular in New Zealand. You can even use Hadamard transformation. You have the distances or the sequences. You use Hadamard transformation. You get new distances, for sure. And question is, are they any better? Do we have more epsilon splits then? Sometimes they seem to be, but so we are not dependent on which distances we use. Model assumptions can allow us to interpret sequence data in terms of distances, and we don't care how you do this. Whether your model is sort of a spherical horse model or something, or the Chinese model, or rather Eratosthenes model. I don't mind. You give me the distances, I tell you what you can conclude just from the distances themselves. And again, like Tandy said, there's marvelous mathematics behind her methods. Also, there are some very beautiful mathematics related to analyzing just the tight spring construction, nothing else. Thank you. Yeah, there's something waiting outside.
That's right.
I don't need water now, I can get wine.
So, yeah, I'd like to thank you all for coming today. It's been very nice. Of course, I'd like to thank the 4 speakers for such interesting and diverse talks. I'd like to thank the London Math Society and the Isaac Newton Institute for also allowing us to host. And I'd like to thank Elizabeth too for making a wonderful job of organising all of this, and I hope you enjoy the session after. So thanks very much.